Dear students, the first two modules introduced you to the concept of computing and assembly language programming as well as memory organization. We also discussed the operations with instructions and data stored in the memory. In real-time applications, the input to the computer need not come only in the form of instructions stored in the memory. So in some cases, it is not mandatory that the computer need to take the inputs in the form of an instructions. Instead of that, some mechanisms like input may come from a sensor switch, a digital camera or microphone and so on. Similarly, output may be a sound signal sent to the speaker or a digital coded signal in order to run a motor or to cause a robot to move and so on. Thus, a general purpose computer should have the ability to exchange information with wide range of devices in different environment. So in the present video lecture, we deal with various ways of input as well as output operations. In short, I can say that I/O operations in detail. So the question comes, how we can access the different I/O devices. A simple arrangement of connecting I/O devices using a single bus. So basically we can consider all the I/O devices are connected to a single bus. The processor memory and all the I/O devices are connected to the common bus. The bus consists of three set of lines, like we can say that the first one is the address line, the second one is the data line, as well as the third one is the control line. So we can have different set of lines like address line, data, as well as control lines. Since there is a common bus, if more than one device is enabled at a time, so we are having only one system bus to which many number of I/O devices are connected. But the question comes, if more than one device is enabled at a given time, the data on the bus will be that is nothing but there may be a problem of contention. So that contention we can call it as bus contention. So there may be a chance of contention that may occur within the bus if more than one device is enabled with respect to a single system bus. So that is called as bus contention. Hence, to avoid this bus contention, each I/O device is assigned with a unique address. So individual I/O device will be assigned with the unique address. Only the address device is enabled and responds to the commands issued on the control lines. The processor can request either a read or write operations as per the address or unique address which was assigned to the individual devices. So now the question comes, how we can access the I/O devices. So as I mentioned before, all the I/O devices are connected to a single system bus, and each I/O device will be assigned with a unique address, or I can say that unique set of address. Bus consisting of three set of lines in order to carry the data, address, as well as control signals. When processor places an address on the address lines, the intended device responds to the command. So initially the processor will place the respective address on the system bus, and the intended device will respond to that command. The processor requests either a read or write operation. The type of request by the processor may be either read or write operation. The requested data are transferred over the data lines. The requested data, irrespective of the type of request, may be either read operation. The type of the request may be either read or write. Read or write. Whatever the type of request, either the request may be either read or write, the data will be transferred over the data lines. So now here we can observe that all the IO devices, we are having IO device 1, IO device 2 till IO device n. So we are having total n IO devices which are connected to a single system bus, and the processor as well as memory is also connected to the single common bus. The processor, memory and all the IO devices are connected to the common bus or single system bus. This bus consisting of 3 set of lines in order to carry the data, address as well as control lines or control signals. So now the question comes, how we can assign address to the IO devices. Generally, there are two ways to deal with IO device. The first one is memory mapped IO. In the case of memory mapped IO, the memory and the IO devices share a common address space. So in the case of memory mapped IO, memory as well as the IO devices, so in our case we considered around n IO devices. So those IO devices will share a common address space along with the memory. Any data transfer instructions like move, load, store, etc. can be used to exchange the information. So in order to exchange the informations, we can directly use the data transfer instructions like move or else load. For example, you can consider one simple example, that is move data in comma R0. So in this case, we use the data transfer instruction move itself, and which will copy the data or which will transfer the data from data in to the processor register R0. This instruction sends the contents of location data in to register R0. Here data in is a input buffer register of the keyboard. So as I mentioned before, we are having two ways to deal with IO devices. The first one is memory mapped IO. The second one is IO mapped IO, or we can also call it as standard IO. So it is also called as standard IO. You can also call it as standard IO, is used by many processors. So in this technique, memory and IO address space are different. So memory as well as IO device address spaces are different. Also, special instructions named as in and out instructions can be used. So here in the instruction we can make use of in as well as out. Such special kind of instructions can be used in order to exchange the data. That means in order to perform the data transfer with respect to IO devices. The advantage of separate IO space is that IO devices deals with lesser address lines, resulting in small decoder size and simpler hardware. So since we are having smaller set of IO devices and we are using external address space in order to assign or in order to name the IO devices, which may result in smaller set of decoder size as well as simpler hardware. Also, there are only two instructions can be used with respect to IO devices, which leads to better programming environment. So we can make use of special instructions like in as well as out instructions in order to transfer the data between the IO devices. So we can say that since we are using only two instructions with respect to an IO devices, which leads to a better programming environment. The instructions like move, load, store, etc. cannot be used to communicate with IO devices. Separate IO address space does not necessary in order to separate the address lines on the processor bus. The same address bus which is used with memory is used for IO devices also. A special signal on the bus indicates whether the sent address is for the memory or IO devices. The user can access the devices connected to the processor in order to access the IO devices. High-level language like C also supports this method of IO interfacing by providing instructions like import, output, etc. So now we'll consider address decoder. The address decoder enables the device to recognize its address when this address appears on the address lines. So what is the task of address decoder? The address decoder it will recognize the address decoder it will recognize the address which was placed by the processor on the single system bus. And the next one is status register. The status register contains some set of informations relevant to the operations of IO devices. So the status register contains some set of informations which are relevant to the IO device operations. So next one is data register. As the name specifies, the data register holds the data being transferred either from the memory or from the processor or into the processor. So here basically we can use two types of buffer registers like data in as well as data out. As we know that the data in is input buffer register which is associated with the keyboard, and data out is a output buffer register which is associated with a display or a printer. The basic functional blocks of an IO interface are address decoder, control circuits, data, status and control registers. In addition, depending on the application, the functionality can be increased by considering a small ROM or else RAM along with a timer as well as interrupt logic circuits. So in the diagram, which shows a simple IO interface to connect an IO device to the bus. So that is nothing but IO interface for an input device. The address decoder decodes the address decoder which will decodes the address which was placed by the processor, which will decode the address on the bus which was placed by the processor so that which will enable the input device, that means the respective input device. The data register holds the data being transferred either from or to the processor. So this data register holds the actual data which is to be transferred either to the processor or from the processor. So next is the status flag register which holds or contains whether or which indicates the status like whether the buffer is full whether the buffer is full or empty, which are used by the processor to verify the status of the device. The speed of the processor and IO device may vary. Why? Because the speed of the processor is very fast compared with an IO device. Also, since IO devices are manually operated, in many cases like keyboard, for example, keyboard is also an IO device. So there not be a synchronization between the CPU operation as well as IO operations. So in order to match the synchronization, or in order to achieve the synchronization, the different IO operations, with respect to different IO operations, so we can consider three mechanisms which are developed for interfacing IO devices, like program controlled IO. The first one is, in order to maintain the synchronization, we are having the first one is program controlled IO. The second mechanism is interrupt IO. And third one is hardware controlled IO. Third mechanism is hardware controlled IO. So we can have different mechanisms like program controlled IO, interrupt IO, and hardware controlled IO or direct memory access DMA in order to perform the different IO operations for interfacing IO devices. So first we'll consider program controlled IO. Consider a simple example of interfacing a keyboard and display to the CPU. We have the flags like, we have two flag registers like N and F out. Associated with FIN is set to 1. If it is set to 1, the status flag register FIN is set to 1, which indicates that a character is entered to the keyboard, and once the processor reads the character, once again FIN will be set to 0. Similarly, F out is 0. F out is equal to 0, which indicates that the display is busy. When F out is 1, the display is ready to receive a character. So F out is 0, that means display or output device is busy. If it is 1, F out is equal to 1, that means the display is ready to receive a next character. In the case of program controlled IO technique, the processor repeatedly checks the status flag. So the processor will repeatedly checks the status flags to achieve the required synchronization between processor and IO. So here, as I mentioned before, the speed of the processor is very fast compared with IO device. In order to maintain the synchronization, the first technique used was program controlled IO, in which it maintains two set of status flags like FIN and F out. The processor repeatedly checks the status flag in order to achieve the synchronization between the processor and IO device. So we say that the processor pulls the device. In reverse way, we can say that the processor itself pulls the device by checking the status registers. That is, the processor pulls the device. This method has the drawback that the processor wastes its time by checking the status of the devices before the actual data transfer takes place. Simply the processor is checking, I can say that the status of the IO. Status of IO devices. So that the processor wastes its time while checking the status of the IO device before the actual data transfer takes place. So hence other techniques have been developed so as to use the processor efficiently. So we can consider an example of IO operation involving a keyboard and video display, and we can use the status registers like status registers which contains the flag which contains the status register which contains the flag register like I can say that FIN, Fout, and along with that we are using two additional flag registers like KIRQ and DIRQ. KIRQ and DIRQ. So this is the registers used in the display and keyboard interfaces. So these two additional DIRQ and KIRQ which are used in order to enable an interrupt. So next one is interrupt IO. IO devices initiates the action instead of processor. In the case of interrupt IO, in the case of program controlled IO, the processor pulls all the IO devices. Here IO devices itself initiate an action instead of processor. IO device sends an interrupt signal, that is INTR signal, over the bus whenever it is ready to receive the data, or else whenever it is free, we can say. Like this, required synchronization is done between the processor and the IO device. So in the case of interrupt IO device itself initiate the action instead of the processor. IO device sends an hardware signal called as interrupt signal over the bus whenever it is ready for the data transfer operation. So that the synchronization can be achieved between processor and the IO device. So the next one is DMA or direct memory access. Device interface transfer data directly to or from the memory, continuous involvement by the processor. So in the case of DMA transfer, which is used in order to achieve better speed compared with the program controlled IO as well as an interrupt. So here the device interface, the data can be transferred directly either from or into the memory by the processor. DMA is a technique used for high-speed IO devices. In the case of program controlled IO technique, the processor initiates the action by checking the status of the devices by entering into a wait loop. During this time, the processor would have performed other tasks instead of simply waiting for the device to get ready. Hence, another method was developed where the IO devices initiate the action instead of the processor. This is done by sending a special hardware signal to the processor called as an interrupt. So in the case of program controlled IO, the processor initiates the action by checking the status of the IO devices by entering into the wait loop. So in such situation, the processor is simply wasting the time. So in order to overcome from this, the IO devices can initiate the actions to the processor by sending an hardware signal, and that special hardware signal which is called as an interrupt signal, interrupt signal. So on the interrupt request line. So these interrupt signals can be placed on the single interrupt request line. Single interrupt request line. So the processor can be performed its own task without the need to continuously check the IO device. So the processor can perform some other task instead of waiting to check the status of the IO device. The routine executed in response to an interrupt request is called as ISR. So that means the ISR consisting of set of instructions. So whenever the interrupt is called, the set of instructions executed in response with an interrupt request, that is called as interrupt service routine or ISR. The processor must inform the device that its request has been recognized by sending INTA signal. So that is interrupt acknowledgement signal. When the device gets ready, it will alert the processor by sending an interrupt signal. Thus, by using interrupts, the processor waiting cycle can be eliminated. So the idea of interrupt IO, so consider a task that requires some computation and the result to be printed on a printer. So now we'll consider one example where we have to compute some set of lines as well as the results to be printed on a printer. Let the program consist of two routines. The first one is compute routine. So we can consider two routines. The first one is compute routine and the second one is print routine. The second one is print routine. Compute routine produces a set of n lines as output, which produces set of n lines as output and which can be printed by the print routine. So the transfer of control through the use of interrupt. So we consider two routines, that is compute routine as well as print or display routine. As per the previous scheme, the compute routine repeats the action of sending one line of the text to the printer, waiting for it to get printed by the print routine till all the lines are printed. So if you are using a program controlled IO, the compute routine repeats the action of sending one line of the text to the printer. So it will send one line and after printing that respective line, it can compute the next line. Hence, the processor spends a considerable amount of time waiting for the printer to become ready. So we try to speed up the process by overlapping computing and printing process. So we can overlap computing as well as printing routine. So initially the compute routine is executed to produce the first n lines. So what we are doing is we are overlapping the operations of compute as well as display or print routine. So here what we are doing is the compute routine is executed in order to produce some set of lines till ith line. So whenever and it will generate some n lines, then the print routine is executed to send the first line of the text to the printer. Now instead of waiting for the line to be printed, print routine is suspended and the execution of the compute routine is continued. Whenever the printer becomes ready, whenever the display or printer is ready, it alerts the processor by sending an interrupt request line. So here in the example we can observe that interrupt is occurred at this particular location. Interrupt is occurred at this respective location, that is ith location. So whenever the printer becomes ready, it can alert an interrupt request by placing its request on the single interrupt request line. In response, the processor temporarily suspends the execution of compute routine and it will transfer the entire control over the print routine. It will transfer the control to the print routine. The print routine sends the second line to the printer, suspends itself and gives control back to the compute routine. So here that is how we can overlap the compute as well as print routine, and we can save the time, and we can also maintain the synchronization between the IO as well as processor. Initially, the processor completes the execution of the instruction till ith instruction. Then, processor loads the PC with the address of the first instruction of the ISR, that is print routine. After execution of ISR, the processor has to come back to the instruction I plus 1. After execution of the print routine, once again it will come to the location, that is instruction I plus 1. Therefore, when an interrupt occurs, the current content of PC is put in the temporary storage location. A return at the end of the ISR reloads the PC from the temporary storage location. This causes the execution to resume at instruction I plus 1. When the processor is handling interrupts, it must inform device that its request has been recognized. So, whenever the interrupt was arised by an IO device, when the processor is handling that interrupt, so it must inform the IO device by sending an acknowledgement signal, that is INTA signal. The task of saving and restoring the information can be done automatically by the processor. The processor saves the content of PC and status register. Saving registers also increases the interrupt latency. The interrupt latency is the delay between the time an interrupt request is received and start of execution of ISR. So the latency, that means the delay between the actual interrupt request to the actual service. That means that the delay between an interrupt request is received as well as to the start of the execution of the ISR. Generally, the long interrupt latency is unacceptable because whenever the IO device is request to an interrupt, the processor will immediately need to provide the service. That means it need to send an acknowledgement, that is INTA signal, to the IO devices. So far we considered interrupt service routine as well as subroutine. It is clear that interrupt service routines are much similar to the subroutine in a program, but there is a major difference between subroutine and ISR. A subroutine performs a function required by the program from which it is called. But ISR may not have anything common with the program being executed at the time INTR is received. The second difference is subroutine is just a linkage of two or more functions related to each other. But interrupt is nothing but interrupt transfers is a mechanism for coordination of IO devices. Once the interrupt request signal comes from the device, the processor has to inform the device that its request has been recognized and will be serviced soon. This is indicated by another hardware control signal on the processor bus called as interrupt acknowledgement signal. So we can consider the schematic of interrupt IO. Like, first we can consider input and output device in a single block. So that is interrupt, input, input output device and a single processor, So the interrupt devices, that is IO devices, can request the processor, that is interrupt request in order to acknowledge this interrupt request. So processor will send the IO devices, that is interrupt acknowledgement to the IO devices. So the IO devices can place the interrupt request on the interrupt request line. With respect to that, the processor uses one more hardware control signal, which can be placed on the processor bus, called as interrupt acknowledgement signal. After receiving the interrupt acknowledged signal, the external device will deactivate the request signal.